Hi everyone and welcome to this new video. We continue with the transient response of first order circuit. This is our example 5. We have another RC circuit. We have an independent voltage source VM, 3 resistors R1, R2, R3 and a capacitor, and there's a switch which will be closed at time equals 0. And the values of the components are given here on the right side. What we like to know is the voltage across the capacitor as a function of time and the current through the capacitor as a function of time for time greater than 0. Now we already know how to calculate the voltage across the capacitor, and we can determine the formula for that. But the current through the capacitor we haven't seen in the previous examples, so that will be new for this time. Once we know the VC, we can calculate the current through the capacitor very easily. So let's start with the procedure. What we did was first determine the situation for without the change. So what is the situation for time less than 0? Less than 0. So what is the situation then? Now if you have a time less than 0, the switch is open, which means that there's no current through R1, so basically the circuit is VM R1 in series with R3 in series with C. So that's actually what it is. And once we know that, then we can say, okay, we already waited for a long time. The capacitor behaves like an open circuit, so actually it will measure, or it will have the voltage exactly as VM. Why? Because there is no current flowing through the capacitor. Also, there is no current flowing through the R1 and also no through all R3. That means there is no voltage drop across the R1 or all R3. So the voltage drop across R3 is 0, and also the voltage drop across R1 is 0. That means the complete voltage delivered by VM will be the voltage for the capacitor VC for the initial condition, of course. So that means I will draw the circuit. This condition is for the initial situation. So we have the R1 and we have the R3 and we have the capacitor, which looks like an open circuit. And this is, I will place it for the situation in initial condition. So if you know that, then we have one of the parameters we need for the formula for VC. So what is VC at 0? So initial condition is the VM, and that is 3 volts. Okay, that's very easy. Now for the next part, we like to know what happens for time greater than 0, larger than 0. That means the switch will be closed, and in the meantime we'll again wait for a long time. That means the current through the capacitor again will be 0, but the voltage across the capacitor will be the voltage across R3, because there is no current flowing through R2. I mean, there's no current flowing through R3. So that means the circuit we have for this condition and in steady state is the following. So there's the resistor R1 still in place. Now there's a new resistor R2, and there is the resistor R3, which just don't have any effect. And we have the situation like this, and I will again denote VC for infinity, means for steady state. So what you see is actually the current through the R3 will be 0 amps. Now, which means actually to calculate the capacitor voltage at the steady state is just calculating the voltage across R2. That's exactly the same thing. So we can use voltage divider rule. So what we can say is the steady state voltage of the capacitor is R2 divided by R1 plus R2 times VM. So let's fill in the given values. The 6 divided by 3 plus 6 times 3, and it will be 2 volts. Okay, we already have 2 of the 3 unknowns, because we would like to know the formula for VC, which requires 3 unknowns. You already know that from the previous examples. We need the initial condition, we need the final condition or the steady state condition, and we need the time constant. So let's write it down to clarify the situation in more. Initial value, and this one is the steady state value or the final value. Steady state value. All right. Okay, let's go to the next and final situation, which is the time constant. I will move this a little bit up. What we actually need is, let's look at the circuit as a given, because this already changed to the circle like this, so we need to look at this condition, which is actually after the switch has closed. So we are looking actually between these terminals, and we set all the independent sources off. So we disable or turn off all independent sources, which means the voltage source Vm will be a short circuit. So that's actually a condition we need to take also into account. So what we have, I will draw a new circuit only for the time constant. For the time constant, we have another situation. So the circuit we have now is the voltage source independent voltage will be a short circuit. R1 is still in place. R3 is still, R2 I mean still in place. R3 also, and we are looking between the terminals, and we would like to know the Thevenin resistance, because for RC circuit, the tau is given by R Thevenin times the capacitor voltage, capacity C. I mean, so you need the R Thevenin and C. Now we don't have the R Thevenin yet, so let's calculate that first. R Thevenin, if you look from these 2 points, what you see is actually R3 in series with a parallel combination of R1 and R2. So that's actually the situation. So R3 plus R1 parallel to R2. Okay, let's write it down and fill in the given values. What we have is R3 is 6 plus, and R1 is 3 times, again 6 divided by 3 plus 6. That's actually the formula for parallel combination. So if you want to calculate this, is a 6 plus 2, and that is 8 ohms. Okay, then we know the value of tau, because that will be 8 times, and the value of the capacitor was 50 millifarad, so that will be 0.05, and we get a time constant of 0.4 seconds or 400 milliseconds. Alright, so that will bring us to the expression for VC, almost. So what's VC? Let's write it down. VC, so VC as a function of time is equal to the capacitor voltage at steady state plus capacitor voltage initially minus the capacitor voltage at steady state times e to the power 2t divided by tau. So I will fill in what we have determined. The VC at infinity, so steady state value is 2, we already see that, and that will be placed here, and the VC at initial condition was 3, so I will also use that. So that will be placed here, and then again 2, and then e to the power t divided by 0.4. Now if I simplify this, then I have Vc as a function of time is 2 plus e to the power 2.5 t volts. And that's actually the expression for the voltage. Now we have the voltage expression. The next step, which is much more easy than this part, is the current. So what is actually current? The current, so the capacitor current. So the capacitor current as a function of time, IC as a function of time. The formula for that is C times the derivative of the expression for the capacitor voltage. Now we already know that, and we also know the capacity C, so capacitor value C. So what we can do here is fill in the value of C and use the derivative of the expression we already know. It's 2 plus e to the power minus 2.5 t. Now if you calculate this, we have a 0.05. Now if you take the derivative of that part in the parentheses, then you get, for 2 of course that will be a 0, and it will be minus 2.5 times e to the power minus 2.5 t. That will be minus 2.5 e to the power 2.5 t. So if we simplify this, this will be 1/8 minus 1/8 times e to the power 2.5 t, and this will be in amps. And that's actually the situation for this example. So again, the procedure is exactly the same as in the previous examples for Vc, so the capacitor voltage. Just one step further is going to the capacitor current. So if you want the capacitor current only, so you also require the capacitor voltage to calculate it using this formula. So we will continue with the other examples again using this procedure. So keep in touch, and we'll see you next time. And don't forget to like and to share the video. Have a nice day.